As you can see, we're talking tonight about calls between Go and C, C++, and also how to call Go from dynamic languages. My name is Dave Raffensperger. I'm a software developer at Crew, which is a global nonprofit. You can read about us at crew.org if you're curious. And the primary stuff we're going to be doing tonight is looking at some practical code examples. All those code examples are in this GitHub repository. I also posted it on the meetup slide. And I'm going to post the talk slides as well. So if you're familiar with CGO, hopefully you'll learn some new tricks. If you haven't seen it before, don't sweat all the details. You can always come back to this. So let's look at the first example. How do we call C code from Go? So this is where the magic happens. This is just a regular Go file, but then we have this special import here called import C, and that's the CGO import. And the comment that's above this import C is actually interpreted as C code. So there's a comment within a comment, and then there's these pound includes, and then we're defining here a C function. Really basic function, just add two numbers and print out what we're doing. So the way we call that C function is quite simply to use the C package and then reference the C function, c.add. And then we can print out the result. And then we can also call functions that were in a library that we pound included. So one example would just be something from the C standard IO library, puts. So we can call puts here with a string and print that out. One caveat here, whenever you're calling from Go to C, you have to be aware of the difference in types between C and Go. So for instance, the string, Go has its own string structure, whereas in C, a string is essentially a null-terminated array of bytes. And so what Go has done is they provide a couple of nice wrapper functions here. The C string function converts a Go string into a C string, a null-terminated string. And there's a corresponding Go string that takes a C string, turns it into a Go string. But the tricky part here is that C string is actually allocating memory on the C heap. And that's outside of Go's automatic memory management. So we actually have to free this memory, just like we had done it with malloc in C. So what we can do is we just call, again, another C function, c.free, and we want to pass in a void pointer, essentially. So in Go, that's considered unsafe.pointer. So we cast that to unsafe.pointer. And a nice idiom, you may have seen this in Go and other places, is to use defer when you're doing cleanup. So here it's really trivial. We could have just swapped those two lines with no problem. But if you had a bunch of things going on down here, multiple exit points from the function, it's nice to call defer to make sure that however you exit the function, you'll make sure to call free. And you can also group the allocation right with the free, so it's conceptually connected. So let's go ahead and run this and see what it looks like. So we just do go run main.go. You can see the output there. So it's doing the addition, it's getting the result, and it's printing. So cool. In a nutshell, that's how you call C code from Go. But let's look at the reverse. How would you call from C back into Go? So let's say we had an adder, but this time the adder is going to call back to Go with the total. So what we're doing in our main function is we're saying add and give Go the total. So we're just passing in those two numbers, and we want C to call this function give Go total with the total. And so the way we can expose a Go function to be callable to C is we have this import C, that clues Go in that we want to use the CGO. And then there's another special comment, this / export. And what that does is it tells Go that we want to expose this function as callable from C. So then here's what it looks like from the C code side. So we've got this add and give Go total. That's the function we're going to call. And what we have to do is we pound include this underscore CGO export. You can see Vim here is complaining. It says CGO export file is not found. And the reason it's not found is because it's actually auto-generated by Go. So whatever functions you have in your exports, Go is always going to regenerate that file as it in its temporary work directory as it builds your project. And so you don't have to worry about that warning, but it's just interesting to know that. And then to call the function, we just quite simply say give Go total. So one thing I want to highlight here is that this parameter is also a c.int. It's not a goint. And depending on your compiler, your environment, the cint and the goint could be different sizes. That's just something to be aware of. Whenever you're converting between Go and C, you have to be aware of this difference in the type system. So let's run this example as well. In this case, what we're going to do is we're going to run go build. And what that does is it builds not only the Go files, but also any C files or C++ files as well in the directory. And then here we got this output to C and back. And there we see, okay, we're calling C to add the numbers, and then C gets the call, and then we call back to Go with the answer. Do you have a question there?
Yes, that's all statically built into C and back.
Yes, it's all statically built in. The examples we're going to look at tonight, except for the interpreted languages, are all going to be statically compiled. There is an example in the repo I shared of calling a dynamic C library, and there's some special tricks to that. I just don't have time to go into, but it's in there. Yeah.
Is this Go 1.5?
This is Go 1.5. This type of thing should work in previous versions of Go. Some of the other examples we're going to see take advantage of the new Go build modes, but this is just the basic C Go stuff that we've had for a few versions. So anything else? Or all right, so let's take this a step further. What if we wanted to call C++? So here's an example of C++ class. Now, in the C++ class, there's this method distance to. So say we have a point, we've got an XY coordinate, constructor, destructor, we want to take a distance to another point. Now you could imagine in a C++ library for geometrical objects, there could be distance to for circles, polygons, all kinds of things. So when C++ generates object code, it doesn't just generate one distance to. It generates a distance to in the context of that class, that template, that function overloading that you're doing. And so C++ does some extra decoration to the symbols in the object file. Some people call it name mangling, kind of a negative term, or name decoration. And so that means, though, that Go cannot call directly into C++. What we can do, though, is we can create a C function, and we can use a special indicator, extern C, to tell the C++ compiler, hey, export these symbols, just ordinary symbols, and then you can call from Go to C and C to C++. So that's how you can call C++ with Go. Or sorry, yeah. So what you could do is you could write that wrapper by yourself. You could write a C wrapper function for your C++ class, and then you could write a Go wrapper function for your C code, and then call Go, your Go wrapper. But there's a tool called SWIG that automates some of this for you. So if you go to swig.org, you can see sort of all the different options that SWIG has. You can do type mappings, like standard string to Go string, and there's a bunch of different things you can put in a SWIG interface file. This is sort of a minimal SWIG interface file. We're just saying we just want to create a SWIG interface for the point class, point.hxx. And so what else? This point package is considered a Go package. And in order to tell Go that it is a Go package, I need at least one .go file, because otherwise the Go compiler complains. It's like, this is not a Go package. So we just have this one thing, package point. Other than that, all of the files in this package are C++. So here's the definitions to these functions. It's basically printing out that we're constructing it, printing out that we're destructing it, and then we calculate the Euclidean distance between the 2 points. So what's interesting, though, is that we could use this package with C++ and SWIG from Go and pretend like it's a Go package. So here's what it would look like to sort of pretend that it's a Go package. It is a Go package. So we're including this package. It's really long because it's part of this examples folder. But then what we're going to do is we're going to say we're using this SWIG wrap C++. And what SWIG's going to do for us is it interprets the constructor, and it's going to create a Go function called new point. So we're going to pass in the x and y coordinate to new point. That's kind of an idiomatic way. Go is not exactly object-oriented, but that's sort of an idiomatic way of having something like a constructor, is say this new point. And similarly to that C example, we need to free the memory that we allocate with new. So there's a corresponding delete point. And then we'll create a second point, and then we can calculate the distance to. Now, one thing that's different here is you notice a capital D. The reason SWIG did that is because you probably are familiar, to export a function in Go, you have to capitalize it to make it public. So SWIG converted that, but other than that, that's just our distance to function. And we're calling this auto-generated Go code that's calling auto-generated C code that's calling our C++ code. So it's kind of a long chain, but it works. So let's do Go build again. We're statically building it in, and then we can run it. Oops. Okay, so here we've got, it's calling a C++ wrap code. We're constructing the 2 points. That's from C++. Then C++ is finding the distance. Go gets the distance back, square root of 2 between these 2 points. And then the defer calls are executed in first in, last out order. So we destruct first 2, 2, and then 1, 1. So, sorry.
So if I'm interpreting this correctly, the Go toolchain is automatically calling SWIG. It's not. You don't
Yes,
have to...
it's automatically calling
Okay.
SWIG. So that's what I want to get into next. Actually, is what is Go really? What is the Go toolchain really doing? So if you use go build -x, that shows you all the commands that go build is running. So it's kind of hard to interpret here, but there's a lot going on. But somewhere up here to the top, you can see this is the temporary folder that go build is using. And then right here is the call to SWIG. And so this SWIG call is taking that point.swig.cxx. So the go build toolchain automatically interprets .swig.cxx and .swig as SWIG interface files. And if it's .swig.cxx, it passes that little -C++. And that's the indicator to say, hey, this is a C++ sort of name-decorated environment. We need to make sure we're careful about how we export the symbols. So go build is taking care of that. But what I want us to do is actually sort of get into the innards of what Go is actually doing here and look at some of that auto-generated code to better understand sort of how SWIG is working. So there's another call we can do is go build -work. And what that does is it outputs the temporary work directory, but it also keeps it around. So you can then CD into that work directory and see all the temporary files that Go is doing. So if you think back to that example where we called from C to Go, and we included that H file that didn't exist, well, that H file would be one of the files that would be in this auto-generated code. So let's take a look at that auto-generated code. So you guys might remember the cgo export.h. There's not really anything in here because we're not exporting Go functions, but it's in this. It's one of the temporary files. So what we're going to focus on here is let's first look at this pointwrap.cxx. So you can see here it says this file is automatically generated by SWIG, and it's not meant to be human readable, but we're looking at it. And it says the source is that SWIG interface file we made, the point.swig.cxx. So I'm just going to kind of move through. This is a bunch of boilerplate code. It's pretty similar between different calls. But here's where it kind of gets interesting. So we're including our class declaration, the point.hxx. And then here's the thing I talked about before, this extern C. That's telling the C++ compiler, hey, all the symbols in here, these C functions, I want you to export them when you create the object code. Don't mangle them at all, just regular names. And then we can call those functions from Go. So what are these C functions doing? So here's one that's this wrap new point. It's taking two parameters, the x and y coordinates, and it's calling new here with the point, and it's returning it. It's got some other wrapping going on, but that's essentially what it's doing. And then similarly here, there's a delete point. That's our C wrapper function. It calls the delete with the argument. And then here we've got wrap distance 2. And this takes 2 points as arguments. And it's going to call distance 2 on the points and then return the result. So that's sort of step 1 of the wrapping. We're wrapping C++ with C. And so we can export the symbols and make it callable from Go. But the second step is generating this auto-generated Go code. And here we've got the source is point.swig.cxx. It's auto-generated. And here we've got the cgo preamble that we saw from the other examples, this import C. And then what's going on here is those C wrapper functions I just showed you that are making the calls to the C++ code, we're including those here with extern references. So then we can call it just the same way we were calling C in the other examples. But this is just auto-generated code. So let's take a look here. So this here is a new point. So that's the function we called in our main function, sort of the pseudo constructor for the point. And what it's doing is it takes the inputs and it's calling this C wrapper function. And it's using the same cgo syntax. It's just saying c.wrap new point with the hash on it. And then it's doing what I talked about before. It's converting the float64, which is a Go type, to c.double. And those should be also 64-bit floating points, but in principle, they're different types. So it's casting it to that. So that's the new point. And then here's the delete point. So it's doing this very similar thing. It's calling the C function that's wrapping delete. And then here's distance 2. It's taking this SWIG pointer, and it's calling the C wrapper for the distance 2 function. And it's passing in both the first argument to the function, which in Go is sort of like what comes before the dot, and then it's the second argument is that other point. So it's passing it in as 2 arguments to the C function, and then here's our Go point interface. So all that is basically auto-generated code, and sort of there's a trade-off here. So the advantage is if you're going to change your C++ code a lot, you can use SWIG, and you add a new function to your class, bang, you can call it from Go without having to rewrite the wrapper. The disadvantage is if something ever goes wrong, you're paging through these ugly files. So there's sort of a trade-off there, but it's cool to know that that's something you can do. It's something in your toolbox to be able to call C++ in this way. And I show another example of what it would look like to just write your own wrapper for C++. So do you have any questions at this point? Or yeah.
I'm sort of what I'm waiting for. Probably you're going to talk about this later, but you already alluded to the heap being different.
Right.
And the concurrency is the thing that I'm really kind of curious how it plays.
Yeah. Let's make sure we get to that. I want to cover before I jump into the performance of the concurrency. But let's first just jump into another kind of fun aside, which is how do we call Go from an interpreted language? So to call Go from an interpreted language like Ruby, Node.js, Java, Python, essentially it's very similar to how we'd call Go from C. So we do this import C, we've got this export add, and then we need our main function. It's not required, but Go just complains we don't have it. And then we've got a make file here. We're conditioning on the operating system for the extension. And then here's where the magic happens. This is new in Go 1.5. This build mode C shared. There's a similar build mode C archive to do a static callable C library. And this one, it's a dynamic library. And then to call this, say from Ruby, there's a Ruby FFI gem you can include. You say where's the dynamic library, you attach the function, and you call it. So I'm going to run make here. So it calls Go build. And then one thing I want to show as well is it's going to actually generate a .h file for the Go code, and that defines the different Go types. And then it's going to have our add function. So if you wanted to call this dynamic library from C, you already got an H file you can include that's automatically generated. So then let's just run these examples. So we've got all these languages calling Go, the addition function, they all get the result. So you can look at the details of how you do that.
Do you use C types in Python?
Yeah, it uses C types. Let me find the Python example. Yeah, it uses C types here. So use C types, and yeah, again, a little conditioning there, load the library, and then we call it. So yeah, there's an FFI thing for Node.js, Java. There's a couple different ways to call native. I use the JNA, that's a little easier. So that's how you call Go from dynamic languages. And so let's get into what you were talking about. What's the performance and concurrency implications of all this? So there is a cost to these cross-language calls. And a call from Go to C is about 50 times slower. And on my machine, it took 160 nanoseconds. I have a benchmark in that folder that calculates this. Whereas a regular Go call to a no-op, you can actually force Go to not inline functions and do a proper benchmark. So a regular Go no-op call is about 3 nanoseconds. And the reason for that is that the Go runtime has a slightly different type of stack than C runtime. There's kind of a switching cost involved. And similarly, for instance, for Ruby, it is about a 30 times slower than a pure Go call. But with something like Ruby or Python, Java, potentially, you could get a speed up from Go if you're calling a compute-intensive function. So don't be afraid of the cross-language call, but don't call them in a tight loop, because that will be slower than making the loop in Go itself. So what about concurrency? So this is where it also gets interesting. So Go has these nice feature of Go routines. You can just very easily multiplex a whole bunch of these Go routines onto a limited number of operating system threads, Go max prox threads. But the caveat comes when you're calling C is that once a Go routine enters CGO, and for 20 microseconds in the current interpretation, it's considered blocking. It's like as if the Go routine is trying to open a file or a network connection or something, for all it knows. And so that blocking C code, which could actually be running compute, it thinks it's blocking. That's not counted towards the Go max procs limit. So we might have to create a new operating system thread. So I did some benchmarks of this, and you can see the code. So I did something where I had 8 Go routines, and Go max procs equals 1. And I did a compute-intensive workload. I split it up evenly between the 8 Go routines. They're all calling C to do the work that's going on. And what happened was, when I just ran pure Go with 8 Go routines, Go max proc 1, it only used 1 CPU core. But now it used all 8 cores because it's spinning up new operating system threads for all 8 Go routines. So that was a case where sort of an unexpected extra concurrency came about. But here's where it kind of went wrong. So I tried 800,000 Go routines, and with pure Go, there's no problem because it's multiplexing those 800,000 Go routines onto a limited number of operating system threads. But with C, it thinks those are all blocking, so it keeps allocating new ones. So I got pthread create fail. So basically, the operating system said, I'm not going to give you 800,000 operating system threads. It's too much resource intensive. So you can still do a lot, but so that's kind of the concurrency and performance implications. So yeah, I want to finish up here for questions, and then if you want to, we can dive into different things as we have time. So yeah, any questions at this point?
Yeah, sure. Is this into the Go test coverage profiling tools?
In terms of the benchmark?
Yes.
Yeah, so I'll show you the example of the what the benchmarks looks like. So the Go no op. So I've got this main test. Yeah, so it uses the Go benchmark, and so we've got this Go to C no op, and we've got the Go only no op. And so the run benchmark, this is where we just say we're passing that. That's a magic compiler flag to say don't do inlining, and we run the benchmark. So let's go to run benchmarks. So so 151 nanoseconds for the Go to C call, and 3.13 nanoseconds for the pure Go call with inlining disabled. If you enable inlining, it's a lot less because it just inlines the null. So yes, it does. That one does. Some of the other benchmarks I didn't. I just used time, and I ran different like the Ruby ones and some of the other Go ones. So yeah, they don't all use this, but the no-op one does.
When do people find it necessary to call C?
Yeah, I think there's a lot of things. So one example is the end of last year, people did a study of GitHub, and about 1% of repositories were in Go, and about 3% were in C, and about 4% were in C++. So right there, you've got 7% of GitHub repositories are in C or C++. There's a lot of scientific computing. What got me into was a linear programming optimization library that I cut out of the talk for sake of time. So a lot of those types of pre-established algorithms that somebody really has thought about this for years and written a really good C or C++ library for it that you could rewrite in Go, but you'd be wasting a lot of time. You could just call it easily. So that's one example. You may have a legacy C code that you want to rewrite in Go, and you're like, okay, well, let's rewrite part of it and call it, and then so you could. That's another example. So.
Have you run into sort of like memory manage issues with calling C and Go with the garbage collector? Because I can imagine there's some cases where you may, well, I just know one example. I tried to pass in an object so I could have C call back Go and be able to reference that object. And it got garbage collected. Do you have any interesting ideas or thoughts on how?
Yeah, I'll show you. I'll show you one thing that's kind of related to that, which is this is the linear programming example. I didn't have time. But somebody asked about calling a dynamic library. This is sort of the way you're passing in things to link to a dynamic library. So this is an example I didn't really get a chance to go into, but one of the things that it has is, so I'm wrapping this C structure, a C pointer, to a linear program, basically. And I actually set up a finalizer. So in this new LP, I call here this c.make LP, okay? So I'm allocating memory on the C heap, all right? But this is actually contained in a Go structure, this LP struct. Now the Go structure itself is under automatic memory management. So Go is free to garbage collect that. So what I could do is Go provides a finalizer So I could say in the Go finalizer for my wrapper Go object, go ahead and delete that C object. So what you could do is you could wrap all your C allocation in these sort of Go objects, and then the finalizer could then, as they're deallocating, to clean it up. Yeah.
Is that kind of wrapping that SWIG would generate for you if you asked it?
SWIG, so in the example we saw, SWIG generated an explicit delete point method, so you had to call that delete point. To my knowledge, you can't. SWIG doesn't offer the opportunity to do a finalizer type thing. Maybe if you hacked it, you could figure out a way. But the way SWIG did it is it just very rotely said, here's your constructor, here's your destructor, because this is kind of a specialized thing. The other thing was
finalizers aren't reliable.
Yeah,
They're like Java. They may run.
Yeah, this is the other thing. This is where I was going to get to. So here, for my example, to force the finalizer to run, I called the garbage collect 3 times. So it's kind of like, it'd be something that'd be good to, if you have a large application, this could be a cool technique to try to help you get around it. And maybe if your C structure is not too big, it'd be okay. But yeah.
Sorry, I didn't interrupt you.
Yeah. So basically, like what Kent said, your mileage may vary with the finalizers, but at least it's a cool idea, and maybe it's worth trying depending on your situation.
So I understand the time constraints, but I was actually interested in this part of the talk. Is this content available?
Yeah. So I'll just pop ahead. So this is I'll just give you the 30-second one. So this is what got me into CGO, is wanting to do a linear program in Go. So linear programming, really simply, you've got continuous variables, you've got linear constraints. It forms basically those constraints, hedge it into like a polygon or a polytope. You want to find the objective function, and then there's an existing library, LPSolve, that I used. And then to call it, you just, the tricky part is you want to make sure make sure that Go can locate the library. So the trick here is these LD flags and passing in the library. And I actually, for Mac, I installed with Mac ports. And so there's you can actually specify a build constraint to say on Darwin, do these, link it to this library. On Linux, link it to that library. Then there's I just do some basic wrapper functions for like adding constraint, setting objective function. One interesting thing here, real quick, is let's see here. To pass an array to Go, you can actually pass the address of the first element. So we're taking in a Go slice here, the row, and we pass in the address of the first element. So I'm sorry, I wanted to talk more about it, but as I practiced it, it wasn't going to fully fit in the time. So yeah, I want to be respectful for our next speaker, but me.
I'm just curious to know, does SWIG help us call Go from C++ as well?
I'm not as familiar with that. My understanding is that SWIG is designed to create wrappers for C and C++ specifically, not just for Go, but for a bunch of other things. Like we were talking about Python, variety of other languages. So its specialty is wrapping C and C++ for dynamic languages or Go. So my understanding is, Kent, did you have a thought on that?
Basically you can make it work.
And I assume you have to go back the other direction. C++ called C and C called Go.
I think what happens is you're going to control it from Go, but you can construct it so that C++ can call into Go once you've done that.
All right. Awesome.
Maybe you know this already, but I noticed in your CGO flags at the top, for Linux you have a relative path. In Go 1.5 they added a special
source thing.
variable.
Yeah.
So,
Yeah, I saw that, and I hadn't fixed it yet. But yeah, that's good. That's a good call.
Just curious if you had time to play around with channels in relationship to any of this.
I did not play around with channels, but I'll show you what I did do. So let's get back to my extra window. So for the Go concurrent one, what we've got is, it's not a channel, but it's this weight group. So you're basically saying, okay, here's all our Go routines that are calculating different parts of this sum. And what we need to do is we need to to say how many are in the weight group, and then we're going to weight on the weight group. So we can do we're having them all do parts of the sum, and then we're pulling together the parts of the sum. It's basically calculating a harmonic series. So it's not a channel. You could do it with kind of a way with a channel, but they have this nice weight group thing for this particular situation. So, all right. Well, thanks, guys. I'm happy to chat with you later afterwards. But yeah, I want to give the floor to Ken. So.